Okay, so good morning to all and welcome to lecture number 20. Particularly in this lecture, we'll be talking about shape feature based on region only. Okay, in the last lecture, we talked about shape feature based on contour. Some of the features were based on contour and some of the features were based on the region. But now, in this talk, we'll be talking about the shape feature based on entire region. So we have seen that earlier, region-based features are like, for example, area, calculating the area, then eccentricity, and so on. So like that way, in last lecture, we have talked about those features based on the region. Now we'll continue with that one. So in today's lecture, we'll talk about the eccentricity, rectangularity, as well as direction, and then compactness of the object. And finally, we'll talk about the moments. So moment concept is basically borrowed from the physics, and this is used in computer vision for extracting the shape feature. So we'll take one example on the moments also. So this is today's agenda. So let me start with the simple features of region-based, like eccentricity. So as I told you that in region-based, entire region is considered. So pixel, within that region, entire region are considered to extract the shape feature. So this eccentricity is one of the region-based feature in which basically what we do, eccentricity is the ratio of length of short axis to the length of long axis of the object. So basically, minor axis to the, it is the ratio of minor axis to the major axis. Means, you see, if you have given a shape, and then from that shape you have to find out the minor axis as well as you have to find out the major axis. So definitely, so this numerator will be less, and then this one denominator will be larger. Okay, so this value, eccentricity value, will be, suppose for example, if minor axis and major axis are same, then that value, this ratio will be 1. But if minor axis is smaller, and major axis is larger, in that case this value will be in between 0 to 1. If it is less, basically 0, then whatever may be your major axis, so this eccentricity value will be 0. So like that way, the result of this eccentricity will be in between 0 to 1. Sometimes this is also called as the ellipticity. So this is, suppose for example, this is the shape, and then the pixel under means within this shape are considered to find out the shape feature. So this is your major axis and this is your minor axis. So definitely, you can find out the eccentricity from this one. So also you'll get this. Sometimes also, okay, it can be defined in the reverse way also. That is the ratio of major axis to the ratio of minor axis. It depends upon, see, if it is ratio of major axis to the minor axis, then definitely it will be greater than 1. And if basically if major axis and minor axis will be equal, at that time it will be 1, and so on. If it is defined as a ratio of minor axis to the major axis, then this value will be in between 0 to 1, and so on. So if it is major axis to the minor axis, this shape will be of having high eccentricity value, whereas this shape will be having the low eccentricity value, and so on. Exactly, it will be opposite if it is defined as a minor axis to the major axis, and so on. Then the next feature based on the region is the rectangularity. Okay, so rectangularity means basically how shape is how much it is in rectangular in nature, and so on. So that you have to find out. So definitely you have to find out the bounding box in that case. So rectangularity is the ratio of object to the area of minimum bounding rectangle. So if fk is the ratio of region area, okay, this is the region area, fk is the ratio of region area, and the area of bounding rectangle. See, that means basically you have given a shape, you have to find out the bounding rectangle. So the area of that bounding rectangle and the area of that shape. Okay, so if area of that bounding rectangle and area of the shape will be same, then it will be having more rectangularity, and so on. So if fk is the ratio of region area and the region and the area of bounding rectangle, so this fk, the rectangle having the direction k, the rectangle direction is turned in a discrete step as before, and rectangularity measured as maximum to this ratio. Means you have to find out the maximum how this shape can be fit in that bounding rectangle and so on, and then this rectangularity measure is measured. So rectangularity has the value of 1 for perfectly rectangular object. Means basically the region area and the bounding rectangle, if that area is same, then that value, rectangularity value, will be equal to 1 and so on. So you have to basically find out in which direction this bounding box fits, and then it will be this. Okay, it will give the value of rectangularity. Next one is the bounding box. Basically, bounding box features, basically the bounding box or bounding rectangular of an object is a rectangular which circumscribes the object, basically. Okay, and the dimension of the bounding box are those as a major axis and minor axis. Means basically here you are fitting that shape in a bounding box, and then you are finding the area of that bounding box. So that area will be equal to major axis length multiplied by minor axis length. So basically all those are the scalar feature. You'll get a numerical value from all those, whether it is a rectangularity, whether it is a basically bounding box, or your eccentricity. So all those are the scalar features. You will get one numerical value out of that one from the shape. Now if you talk about okay, can we reconstruct the shape from these features? Suppose for example this eccentricity. Okay, eccentricity, you'll get the value of some numerical or scalar value from that one. Can you reconstruct that shape from that eccentricity? Absolutely not. So reconstruction is not possible. Only thing is that you'll get some value which can be used as a feature and so on. Now, second thing is that, okay, can we think that whether this eccentricity will be a rotation invariant? I think it will be rotation invariant. So if you, even if your object is rotated in this direction, this eccentricity value will not change. Okay, whether this eccentricity is this one translation invariance. So for example, this object is here, and if you are calculating the eccentricity, so definitely you'll get some value. If this object is shifted here, okay, you'll get same value. So eccentricity is basically a translation invariant, rotation invariant, but it is not this one scale invariant. So for scale invariance, you have to normalize the things, and then you'll get the scale invariance. So these are the advantages of these scalar features, like as eccentricity. From eccentricity you can obtain the rotations, translation, and scale invariance property. But what is the disadvantage? That you cannot reconstruct that object back from those values. So this is applicable for eccentricity. This is also applicable for the rectangularity. So rectangularity is also basically translation invariant, rotation invariance, and you can obtain that one scale invariance by normalizing the things. So whether you are considering the eccentricity or rectangularity or bounding box, all those scalar parameters are rotation, translation, and scale invariance. But one major disadvantage is that from those values, whatever you get the scalar values, you cannot reconstruct that object back. So this is the limitation of these scalar features and so on. So bounding box, see that. So this is the bounding box, means you are just fitting that object in a box. Okay, so this object is also fit in this one and so on. Now the direction, okay, is also another scalar feature. So from definitely this can be obtained as a rotation invariant, scale invariant, or translation invariant. But from that one you cannot reconstruct that object back. So how direction is calculated? So direction is the property which makes the sense in the elongated regions only. So if the region is elongated, the direction is the direction of the longer side of the minimum bounding rectangle. So if the shape moments are known, the direction can be calculated as this one from the moments. Okay, so moments we'll see in our next part. So direction is basically elongatedness and rectangularity are independent of linear transformation, translation, rotation, and scaling. So direction is independent of all linear transformation which do not include the rotation, because rotation direction will change. So translation invariance is there, scaling invariance there, but rotation invariance is not there because you are calculating the angle from that one. So mutual direction of two rotating object is the rotation invariant. Okay. Then the last scalar parameter of this region-based object, region-based features is the compactness. Now, how that object is compact? Okay, so you are calculating the compactness. Okay, so compactness is defined as the ratio of area of an object to the area of circle with the same perimeter. So basically, with same perimeter, you are finding the area of the circle and also area of the object. So compactness can be calculated as 4 pi area divided by perimeter square, or a circle is used as it is the object with most compact shape. Okay, so from this figure you will come to know how this compactness is calculated and so on. So this is basically, see that this is the shape basically. Okay, this is the shape, and then this is the circle. Okay, of same area. So you are taking the ratio of that one. So here also see that this is basically, or in another way also, area divided by perimeter square is also used as a compactness. Okay, this will be, see, circular object will be more compact as compared to other object if you okay, area divided by perimeter square, if you are taking that in that way. So this will be less compact. So compactness, perimeter will be larger in that case, but area will be less. So definitely compactness will be less. So in this case, basically, area is somewhat larger as compared to this one, and perimeter is less. So compactness is increasing. Now, if you are considering the simple this one circular object, so in that case, this object, circular object, will be more compact object because you are considering area by perimeter square as a this one scalar parameter in that case, right? Uh, so see that perimeter square or by area, or area by perimeter square, anything. Okay, only these values will change. So compactness, which have an elliptical shape or a boundary that is irregular rather than smooth, will decrease the measure. So alternate formula can be used as a perimeter square divided by 4 pi area, and the measure takes minimum value of 1 for a circle, and objects that have complicated irregular boundaries have larger compactness. See, you can also define compactness as of area by perimeter square or perimeter by area square. It is up to you. You can define. So only values will change and so on, right? So as I told you that circular object will be more compact as compared to the other objects, right? Irregular object and so on. So this will give you the basically a scalar feature or numerical value of the shape. Now let me know whether this compactness is a rotation invariant. If object is rotated, okay, and if you are finding the compactness, whether this is this compactness value is changing? Absolutely not. So compactness is rotation invariant. If this object is translated here, whether compactness value will change? No. Okay, so compactness is rotation and translation invariant, as well as if you are normalizing the things, you can obtain the scale invariance. Means, okay, if this same shape is there but of small scale, so if you may, okay, normalize the things between the perimeter and area, then you can obtain the scale invariance property of this compactness. So compactness is scale invariant, rotation invariant, and translation invariant. But another thing is that, just think, whatever the value of compactness you get, from that compactness value, can you reconstruct the shape back? Absolutely not. Okay, so reconstruction is not possible. So that is the basically disadvantage of scalar properties or scalar features of shape, which are obtained from the region, entire region, and so on. Okay, so this is all about the scalar features. One more scalar features are basically the moments. Okay, now this is the last feature of based on the scalar type, scalar features, and this moments basically, that this idea is borrowed from straight away from the physics. Okay, so that okay, what is moment in the physics and so on. So this as the entire same idea is borrowed in the this computer vision. So these objects or images are considered as the objects, and then from that objects we can calculate basically what is the moment, central moment, then moment with respect to x-axis, with moment respect to y-axis, then variance with respect to x-axis, variance with respect to y-axis, and so on. So those features are used as a shape features because these values will change. Okay, it depends upon the shape of the object and so on. So for example, if x is the discrete random variable and the expected value of x is denoted by, expected value is nothing but the mean value basically. Okay, e of x is defined as this one, e of x is equal to I, okay, summation I is ranging from 1 to n probability of xi. So that is nothing but the mu x, where this x1 xn are all possible outcomes of x, and probability of xi is the probability that x is equal to xi. Okay, now the expected value of x mu x is thus the weighted average of its possible values, and each value weighted by probability of its occurrence. Okay, now see, this is nothing but the mean value of the this one object and so on. Now if x has the countability infinite range, then the summation is from I equal to 1 to infinity, and the expected value of e of x is called as the mean of x and is denoted by mu or mu of x. Okay, so this expected value is also called as the first moment. Now how do you calculate the mean of the given shape or something like that? So definitely what you have to do, whatever the okay, you have this given shape, and from this shape, okay, in that region there are various values of your this one pixel values. So you have to take the average pixel value okay, within that shape, and this average pixel value is nothing but the mu x value, or this is also called as the first moment of the that object or something like that. So this is again a numerical value or scalar value which can be used as a feature, and this idea is borrowed from the physics. So expected value e of x is called as the first moment of the distribution, and the kth moment of this is defined as see that it may be first moment, it may be second moment, it may be third moment, and so on. So the general formula for x kth moment is given by e expected value of x raised to k is equal to what he has done here. This k is there in the xi raised to k. So this value, see earlier your expected value was this one. Now here this formula is modified with kth moment. What here done, x raised to k, and then here also x raised to k is xi raised to k. So this is added, and from that one, so if you are considering the first moment, so value of k will be equal to 1. So value of k will be equal to 1. If you are considering the second moment, the value of k will be equal to 2. Here also k will be equal to 2. So it will be squared and so on, right? So if you are basically continuing this idea for the image or object in computer vision, so the formula will be changed. So just you have to modify, because you know that in image there are basically two coordinates. One is x coordinate and another one is y coordinate, and from the x coordinate and y coordinate you get the special coordinates, and from that you can calculate the special coordinates, you can calculate the moments of the image. So from the moments of the image, we can find the area or total intensity, that is its centroid and information about its orientation. And the gray label at that pixel is considered as a mass at a point of an object. See that, as I told you, that this concept is borrowed from physics. So when you're calculating the centroid of that one, so for that you have to calculate, okay, you should know the mass of the every point and so on. Similarly, when you're calculating the centroid of or basically expected value of the image or shape, then in that case basically pixel values are considered as a mass value, or pixel intensities are considered as a, so just okay, at every point you'll get different pixel values or intensity. So thus zth moment of an image of f of xy is defined as, see, this is the formula that you have to use for calculating the moments of the image or shape. So mij is the moment, okay, summation over x, summation over y, that is rows and columns, x raised to I, y raised to j, and f of I comma z. Okay, now this I and z will decide the moment. Now see that, suppose for example, if where m10, now you are finding when I is equal to 1 and z equal to 0, then this will x raised to 1 will be there and y raised to 0 will be there. So y raised to 0 means this will be one value, so x raised to 1 into f of xi, so that is nothing but the moment with respect to x-axis. Now if you are considering I as 0 and z equal to 1, in that case this x raised to I will be equal to 0, so this value will become 1, and then y raised to z, that is z is 1, so y raised to 1 will be equal to y, so y into f of x comma y. So this will be the moment with respect to y-axis. So you can find the different values, like for example, if x is equal to this, I equal to 0, y equal to z equal to 0, in that case this value will be equal to 1, this value will be equal to 1, and f of x y, so just you're doing the summation of all pixels, so that will give you the m00, so 0th moment, you'll get the 0th moment. And if you're finding if I equal to 1 and z equal to 1, so that will be equal to moment with respect to x-axis. And if okay, I equal to 0 and z equal to 1, so that this formula will be equal to this I equal to 0, so it will be 1, and z equal to 1, so y into f of xy, so that will be equal to moment with respect to x-axis. And as I said that if this I and z is equal to 0, then this will be the mass of the object represented by f of x comma y. So just you're summing all the pixel intensities, and then that will give you the value of 0th moment, or m00, and this is nothing but moment with respect to x-axis, moment with respect to y-axis. So see that you can find out the different features of the shape, like as moment with respect to x-axis, moment with respect to y-axis, then moment, okay, 0th moment, that is nothing but the mass of the object, or this one. So this is the third feature. Then the fourth features from this moment can be derived as a coordinate of the centroid of that object. So this coordinate can be obtained from this value. See, m10 is nothing but the moment with respect to x-axis divided by mass of the object. So this will give you the coordinates of the centroid, x coordinate of the centroid, and then this will give the y coordinate of the centroid. So this value can be also used as a feature in the shape. Then now when you change this value as I equal to 2 and then j equal to 0 here, so this will be moment of inertia about x-axis. Now what happens basically, if I equal to 2, so this will be equal to x raised to 2, and j equal to 0, so this will be equal to 1. So what will be your formula? Summation over x, summation over y, x square into f of xy, x comma y. So that will be basically moment of inertia about x-axis. So that can be used as a fifth feature for representing the shape. Similarly, okay, if you are keeping this I equal to 0 and j equal to 2, in that case this x component will become 1 and y component will be squared, that is y raised to 2 into f of xy, and then you are summing all those things, so that will give you the moment of inertia about y-axis. So you got how many features from this moment? first one, this one m10, m01, m00. So this third, fourth feature, that is the coordinate of the center of that is one, moment of inertia about x-axis, moment of inertia about y-axis. Okay, and then this we can also define the moment m bar ij, that is about the centroid. It is also called as the central moment. Okay, and so on. So from the shape, you can obtain various features of that object based on the moment. And now again, see that whether these moment features are this one. Okay, whether translation invariant, definitely it is a translation invariant. Whether these features are rotation invariant, okay, we have to think over it. Just look at the following example, how we calculate the moments, and then we can think whether it is a translation invariant, rotation invariant, and scale invariant, and so on. Now consider this image of 4 by 4, and we have to calculate the different moments, like as the mass object, and moment with respect to x-axis, moment with respect to y-axis, centroid of the object, then moment with respect to x and y-axis. Basically, sorry, here there should not be any comma. So this is moment with respect to x and y-axis, that is nothing but the m11. So here, what is this one? Mass of the object, that is nothing but m00. Moment with respect to x-axis is nothing but m10. Moment with respect to y-axis is nothing but m01. Then centroid, you have to calculate m10 divided by m00 and m01 divided by m00. So that you have to get. And then moment with respect to x-axis and y-axis means value of I equal to 0, y equal to 1, and z equal to 1, that is nothing but m11. So x raised to 1, y raised to 1, that formula will be there. So you are finding the m11. And then moment of inertia of object about x-axis means here I equal to 2 and z equal to 0. So m20 you have to find. Then moment of inertia of object about y-axis, that is nothing but m02. And then moment of inertia about origin, also you can find out that one. So these are the different features which you can obtain the based on the moment. Now this is the image. So you know that this is the first row. Okay, so this is the first row and this is the first column. So this first column, second column, third column, and fourth column. So columns are represented by y, and rows are represented by x. So this is f of x comma y. So this is first row, second row, third row, and fourth row. This is first column, second column, third column, and fourth column. And 4 by 4 image is having the intensity like this. So x11, x is 1, y is 1, at that time intensity value is 3. X is 1, y is 2, at that time intensity value is 1, and so on. So these are the intensity values of 4 by 4 image, and from those intensity values you have to calculate the mass of the object, moment with respect to x-axis, moment with respect to y-axis, and all those different moments you have to calculate. Now we'll see solve this problem, and we'll calculate one by one. See that m00, you know the formula for this one, x raised to z. Okay, this mij, general formula of moment is mij, which is equal to summation over x, summation over y, and x raised to basically here I, and y raised to z. Now but value of I and z is 0 0. So x raised to 0, y raised to 0. So what will be this value? So this value will be equal to 1, this value will be equal to 1, and only just you have to do the summation of f of x comma y. So f of x comma y over x and y. Now look at this one. So just you have to do the summation of all those intensities. So what is the summation? 3 plus 1 plus 2 plus 0 plus 2 plus 0 plus 3 plus 1 plus 2 plus 3 plus 1 plus 0 plus 1 plus 3 plus 0 plus 2. So this summation, entire summation of pixel intensity is equal to 24. So this is coming as 24. So this is nothing but the mass of the object. So what you have done, just you have added all the intensities of the pixel within that region, and that is giving the mass of the object. So that is nothing but the m00. So this can be used as one of the feature for representing the shape. Now the second feature is m10. m10 means moment with respect to x-axis. So you know that this is I and this is z. So x raised to I, y raised to 0, y raised to z. Now what is the value of I? I is 1. What is the value of z? That is equal to 0, right? So this y raised to 0 will be 1. So your formula will be equal to what? Summation over x and into summation over f of x comma y. Okay, so here see that how we are going to calculate. Now see that summation of f of x comma y, and then what is the x here? So see that, look at this one, x value is 1, right? So 1 multiply, what is the summation of all those f of xy in this row? So 3 plus 1 plus 2, that is equal to 6. 6 multiplied by 1, so that is it is coming as 1 multiplied by 6. So this is row is 1, and summation of f of xy over y in that row will be equal to 6. So this value is coming, right? Now the second value, what is the value of x? 2. What is the summation value of this row? So 2 plus 3 plus 1. So again it is 6. So 2 into 6. So it is coming 2 into 6. I hope that you are understanding now how you are calculating M10. Then what is the value of x? 3. And what is the summation of this row? Again it is coming 6. So see that here 3 into 6, right? And then the next one, what is the value of x? X is 4. What is the summation of value of this one? 1 plus 3 plus 2 or 0 plus 2, that is equal to 6. So this value is coming 6. So 1 into 6 plus 2 into 4 plus 3 into 6 plus 4 into 6. So this M10 is coming as 60, right? This is coming as 60. So you got another feature, that is moment with respect to x-axis whose value is equal to 60. Similarly, you can calculate the value of moment with respect to y-axis. Now in that case, moment with respect to y-axis, so value of I will be equal to 0 and z will be equal to 1. Now if you put the value of I equal to 0, so x raised to 0, y equal j equal to 1, y raised to 1. So what will happen basically? This x raised to 0 will be equal to 1. So your formula will be basically like a summation over y. So y will be there, summation over y, and summation over x of f of x comma y. Now look at this one. Whatever we have done for rows, similarly we can do it for columns. So what is that? So you are considering y as 1. At that time, y 1 multiplied by what is the summation over this column? 3 plus 2 plus 2 plus 1. So that is coming as 8. So 8 multiplied by 1. So that is what this first value is coming as 1 multiplied by 8. Similarly, when you are considering the second column, so 2 multiplied by what is this summation? So 1 plus 3 plus 3, that is 7. So I think it must be 2 multiplied by 7. Then plus third column. So third column is third column 3 multiplied by what is this one? So 2 plus 3 plus 1, so that is nothing but 6. So 3 multiplied by 6, and then fourth one will be 4 multiplied by 1 plus 2, that is 3. So 4 multiplied by 3, so that is what it is coming. So M01 value will come as 52. Okay, so you got third feature of the shape from the moment, right? Similarly, you can continue that one and even find out the value of coordinate of the centroid. So coordinate of the centroid of the object is given by the formula M10 divided by M00. This is the x coordinate, and then M01 divided by M00, so that is equal to y coordinate of the centroid. So 60 is M10 value, and M00 value is 24, M01 value is 52, and then this M00 value is 24. So that will be to the centroid coordinates. Right now, I hope that you have understood how to calculate this. Now the fifth, this one, what you are doing, moment with respect to not only x-axis and and y-axis, but at the same time, moment with respect to x and y-axis we are calculating. So that's why value of I is 1 and z is 1. So this formula will change as x raised to 1, y raised to 1, that is x into y. So summation over x comma y, and f of xy, right? Now see that how it is calculated, 1 into 3. So see x into y. So when you are considering x is equal to 1, y equal to 1, and what is the value of f of xy at that time? So that is nothing but the 3, right? So how you are calculating here, look at this one, this image. X into, what is the value of x? 1. What is the value of y? 1. So x into y, that is 1. And f of xy at that time, this one 3. So 1 multiplied by 3. So 1 into 1 multiplied by 3, right? So this is the value, it is coming as 1 into 3. Now, so this is x is 1, y is 1. Now we'll continue with that one. We'll keep x is equal to 1 and y will change. So suppose, for example, x is equal to 1 and y is equal to 2. So what will be the value of this one? X into y, that is equal to 2. Now at that time, what is the value of f of xy? See, look at this one. X is 1 and y equal to 2. So 1 multiplied by 2, that is equal to 2. And what is the value of f of xy? That is equal to 1. So 2 multiplied by 1 is the value of this one. So 2 multiplied by 1, right? Now x is equal to 1, y is equal to 3, so it will be 3. And at that time, what is the value of f of xy? So go back here. This is the value, 1, x is equal to 1, y is equal to 3. So 1 multiplied by 3 multiplied by 2. So that is equal to 3 multiplied by 2, right? And then when x is equal to 1 and y is equal to 4, so 1 into 4 multiplied by 0, so that will be equal to 0, right? So I hope that I have written here 4 multiplied by 0. So this is for first row. Similarly, you have to continue for second row, third row, and fourth row. Now see that when you are coming here for the second row, what is the value of this one? X is 2, y is 1. So 2 multiplied by 1 multiplied by 2. So 2 into 2, that is 4. Then 2 multiplied by 2, that is 4 multiplied by 0. Then 2 multiplied by 3, that is 6 multiplied by 3. So 18. So 2 multiplied by 4, that is 8 multiplied by 1. So that is 8. So similarly, you have to continue like that way. 3 multiplied by 1 multiplied by 2 plus 3 multiplied by 2 multiplied by 3 and so on. So like that way you have to continue up to this point. So you'll get all those values like this, right? So this value, moment with respect to x and y axis, is equal to 134. So you got the fifth feature from the moments. Similarly, the sixth feature you can obtain, that is inertia, about moment of inertia about x-axis. So in that case, the value of I is equal to 2 and the value of z equal to 0. So formula will be equal to x raised to 2, y raised to 0. Now what you do, you have to square the value of this one. So summation of square of this one, and then f of xy. How do you calculate that one? Now when you are considering this one, first row. So what is the first row value of this one? X. X value is 1. Square of that one will be equal to what? 1. And what is the summation of this one? 3 plus 1 plus 2. So 6. 6 multiplied by 1. So that will be equal to the first this one. First value of this one, 1 into 6, right? Now second row value will be, what is the square of this one? See that square of this one will be equal to second one. Square of this one will be equal to 2 multiplied by summation of this one. 2 to the square is 4. So 4 multiplied by summation of all those pixels. So 2 plus 3 plus 1, that is 6. So 4 into 6 will be your second value. See that 4 into 6 is your second value. In the third row, what is the value of x? So what is the square of x is 3. Square of that one will be equal to 9. And summation of all those pixels in that row is 6. So 9 multiplied by 6. And in the fourth row, x value is 4. So square of that one is 16. And summation of all pixel is 6. So 16 multiplied by 6. So M20 value, if you calculate, it will come as 180. That is 180. Similarly, you have to continue that one for moment of inertia with respect to y-axis. So that is nothing but the m02. Now when you put the value of as m02, so this formula will change as x raised to 0, because I value is 0 and z value is 2, so y square. Now here you have to take the y square instead of x square, and then summation of f of xy. Now earlier you did it with x-axis, now you have to do it with y-axis. So look at this one. When your y is 1, at that time what is the summation of all those pixels? See that y is 1, square of that 1 will be 1, summation of this one will be 3 plus 2 plus 2 plus 1, that is 8. So 1 into 8 will be the first value, plus what is value of y? 2, square of that one will be 4. So 4 multiply by this summation, so 7 multiply by 7. Then third one will be 3 square, so 9 multiplied by what is the summation of this one? 6, plus 16. 4 square is nothing but 16 multiplied by summation of this one will be equal to 3. So this value is coming as 1 into 8 plus 4 into 7 plus 9 into 6 plus 16 into 3 equal to 138. So you got moment of inertia with respect to y-axis, and then m0 can be calculated as m20 plus m02. So this can be also another feature, eighth feature. So what you got after all from this, also you got the scalar features which are representing, okay, from the region of the object and so on. Now from that one, can you calculate this one, whether these features are translation invariant? So definitely you can obtain the translation invariants and so on. Even if you rotate, you can obtain the rotation invariant features and scale invariant features by this one, normalizing the things and so on. So moments, okay, only thing is that this is also scalar feature, so you cannot reconstruct the object back from these features. Only thing is that you can okay, represent those objects with some scalar features. So these moments are generally widely used in computer vision application for representing the shape and so on. So this is all about the scalar features which are defined from the region of the object. And uh, in our next lecture, we'll be talking about how to obtain the graphs from the region. So for that, we need to study how to obtain the skeleton from the thinning or medial axis transformation. And then once you obtain the skeleton from that, how do you construct the graph? And then how graph-based matching technique can be used in computer vision. So that we'll study in our tomorrow's lecture. So today we'll stop here. And this finishes about the scalar region features which are obtained from the entire region of the object. So that's all from today's lecture.